Okay, let me continue. For the positional encoding, based on the types, we know that there are two types of positional encoding. First is the learn positional embedding, and the other is using the sinusoid. So the positional encoding is a technique used in models like transformer. It is to provide positional information to the model by adding position dependent signals to word embedding. So we want to know where is the position and whether the position is affecting the embedding. It allows the model to incorporate the order of words in the input sequence. So let's say I have the word I am a robot. So the sequence is I, and then M, and then a, and then robot. We can make the index. I will be index 0, M will be in index 1, A will be in index 2, and robot, it will be in index 3. Based on this index, we can make the positional encoding matrix. So the positional encoding matrix will be like this one. We have P00, P01, P02 until P0D. So D, yeah, it refers to the any model. In this case, we have only 4 sentences. And then we have 0, 1, 2, 3. So for every of this one, we can have the positional encoding, and we usually have a number to represent the n. If you look at the, I think this one, we have another formula. So we want to check where is the position or the index divided by a big number. In this case, this is the n. So in the literatures, they fix the number into 10,000, and then we will do the exponent with 2i divided by the D model. So I, for every of this, there will be two kind of things. The first is using the sinus, and the other is using the cosinus. For the position 0, and at the index 2i. So it means in the index 2 multiplied by I, it is in the index 0, 0. Then we will do the sinus. What is the position? And then we will divide with 10,000, 2 multiplied by I divided by the model. Then in this case, we have the sinus position. So the position is 0, okay, divided by 10,000. So yeah, in this example, I think they use 100. And then you do the exponent 2i divided by the D model. So if we remove the 2 digits, so it becomes 100. 2i, 2 multiplied by I, it is 0. Okay. Then 0 divided any number, it will be 0. Then 100 power of 0. our 0 is 1. So any number, when we have 0 divided by any number, then it will be 0. So we got the sinus is 1, 0. Okay. So sinus 0, it is 0. So and so on. So you can calculate. Okay. And we got this matrix. If it is 0, 1, it means we are using the position, comma 2i plus 1. So 2i plus 1 is 1. Then we use the cosinus. So in this case, we use the cosinus. And you will see for every position, we have the I equals to 0, I equals to 0, I equals to 1, I equals to 1, and so on. If it is I equals to 0 for 0, 0, then we use sinus. For I equals to 0, and when it is 2i plus 1, we use cosinus. Sinus, cosinus, and so on. Then we got the number. We got this number. And yeah, you can use this positional encoding for next. If you look at this one, we have this positional encoding, and we will use this positional encoding to perform the next, which is the attention network. I give you the Python code. So if you can open it. Yeah. So this is the code to represent the position encoding. Now let's say that I'm just having a length, which is 4. And then let's make the D equals to 4. Okay, so it means we have only 4 columns. And then we have the N is 10,000. So you can do the matrix generation of this position encoding. Based on the formula, we have the 2 multiplied by I. We use the sinus function. If it is 2 multiplied by I plus 1, we use the cosinus function. Okay. And then we do this with the denominator. The denominator means it is a power function, and with the 2 multiplied by I divided by D. So D is a number that you determine. In this case, the model is 4. So if you run, you get this positional encoding. So this is the positional encoding that we can use for the attention model. So we can also put more. Let's say I want to only plot the sinusoid. So if you want to plot only the sinusoid, let's say, I have the D. Usually the D length is very long. It is to indicate that the word of the sentences might be long, and there are many works to find what is the best D. In some of the words literatures, they mention they can use the 1 to 8, or maybe they use the 256, 512. So it refers to the memory size. Now, let's assume we use the D equals to 512 and N is 10,000. You can plot this one. So K means the length. K is the length of the sentence. And D is how big is the model that you want to create. You can see here, if it is nothing, or the sentence has only 0 word, the position is not that important. But if we have 4 words, so the location or the position will be something like this. If we have 8 words, so the position will be something like this one. If we have maybe this one. we have 12 words. So this is the sinusoid. So what does it mean? We will pay attention to the higher point. In this case, if we look into English word, some of the English words, maybe the first will be only the subject, okay, and the next might be it is related to the verb, and we want to focus on maybe the object or maybe some location. So the focus will be in some of the text after maybe 5 early words, and then if it is very long, there might be some other point that we can focus on. So the higher point, will be a kind of information to the next step, or which is for the attention mechanism. So we can also look at the kind of color bar. Okay. So this color bar means if the length is longer, okay, sometimes we will not, we have a very high value here, okay. But you can see here, this kind of color means we can pay some more attention on this word. But if it is very long, usually we do not have any more attention. There are some works in the research, they say that maybe after 200 words, it is not a kind of less important because of the position. Usually, when you read a kind of papers or news, you will focus on the first paragraph, or you will focus on the summary, or you will focus on the first part. Okay. So those kind of things, they refer to this positional encoding. Of course, this is only valid for some of the domain. It cannot be valid for many other domains. The final output of the positional encoding layer, after we have the word, okay, we will do the word embedding. It means I have the encoding for the I have the factor for the word M, I have factor for the word I have factor for the word robot, and then I will generate the positional factor. Okay, the positional factor, like what we saw before. We have the positional factor for I, for M, for and for robot. And we will do a kind of multiplication or some process between this factor and this factor. At the end, we will get the positional encoding layer. We call this is the positional encoding. Positional encoding, positional encoding, positional encoding for every of the token. And we will use this one for the attention network. This is the paper about the attention in 2017. Those groups from Google and some other institution, for example, it is from the University of Toronto. Okay. So they propose the attention, and this is one of the important research these days, especially in the domain of NLP. For the experiments, okay, in the attention paper, they try to do some experiment about the layer. For example, if they change the self attention, so they try to look at the complexity. If you join the data structure and algorithm class, you may understand the big O notation. Okay. So this is the big O notation. It means if the algorithms run in the square, okay, n power of 2, then it is a quadratic. Then this layer perform very long, or it is computational cost. It is the complexity for every layer, and you can refer to this one. If you look at those layers, all the layers are quadratic, 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 okay. Quadratic. It means it is power of 2. But if it is a self-attention with restriction, so we just focus on some of the attention. So we are not focusing on all the attention. So we have the R. Then the complexity of the layer will be reduced. And we can see this one is a linear type. And we can also look at the sequential operation. So the sequential operation is O1, ON, O1, O1. If the algorithm is running in O1, of course, this is the best. Some of the operations still have ON. So ON is still linear. And the maximum path length, okay, you can see we have O1, ON, O log N, ON divided by R. So it is common for any research paper to discuss this computational time, because when they do this computational time in different computer, the running time will be different. The running time will be different. But if they put this big O notation, then it is the same for every computer, and it is based on the algorithm itself. So if you want to know more about the N, what is N, what is D, what is K, and what is R, okay, so you can refer to the paper about this attention. Yeah, the observation from this paper, the self-attention has O1 maximum path length. Okay. So the self-attention, it has O1 maximum path length. It means we can capture the long-range dependency easily compared to the recurrent. So the recurrent means the RNN. Convolutional. So it is the convolutional neural network using the CNN. And self-attention with restricted. So this is N divided by R. R is the size of the neighborhood in restricted self-attention. So when N is less than D, self-attention has lower complexity per layer. When N is less than D, so the self-attention has low complexity. That's why we use the R. It is to restrict or to limit the complexity of every layer. For the experiment result, yeah, I guess you are also doing your project. Okay. This is the result from the transformer. For the experiment result, you can apply a metric. For example, this is using BLEU. I think you remember the BLEU. This is one of the metrics to understand how good is your model. So we have the reference and we have the generated text. So you need to compare between the reference and the generated text, and we need to get the BLEU score. So this is the BLEU score. Okay, so you can refer to the material on the week 5 or 6 about the metrics. Okay. Yeah, we can see this one. The highest score is the bearer. Using this model, 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 they perform with the data, and then they got this result. And the transformer at that time, okay, in 2017, with the 2014 data, they got 28.4. So it is the highest among the existing method. For the, this is English to DE. DE is English to Germany. ENFR, it is English to France. So they are going to translate the news, okay? And they are checking whether the transformer can translate the text correctly or not. And the blue score for English and French is more or is higher than the English to Germany. And especially when they use the transformer, okay, so it achieves higher. This one is the comparison between transformer and the big. Unfortunately, the conf S to S ensemble, it shows it is highest for the English to French translation. Yeah, if you are interesting in this kind of NLP, you can also try with this training course, or people use the word flops. It means how big is your training cost when you train the model. So they will calculate the training cost. If the training cost is high, of course, it will consume a lot of energy. If the training cost is low, then it will use lower energy. And nowadays, people try to use the lower energy algorithm. If it is lower than the other model, of course, people will choose that one. So those kind of things can be, you can do it in your experiments. So there's also another kind, this one, of the number of operations that you did during the experiment. Okay, so this is the explanation. The English to German translation, a new state of word, and it increased 2 over the BLU score. For the English to French translation, there is a new single model, BLU with the 41, and the training cost is less. Okay. So if you can show like this one, of course, it will be a good result. Not only showing the result on the PLAU, but also showing that your training cost is lower than the other. Okay, let's look at the Google Colab. For this Python code, I combine with the next section, which is about bird. So you can see some of the materials might be mixed. Yeah, this is the code to understand about the attention. You already learned about the skill.product attention. There is a reference for understanding the attention, and basically it is only the matrix multiplication, mat mul, okay? As I explained before, mat mul, it is the matrix multiplication, and we are going to multiply between the Q and the K transpose. Okay, before I mention T is transform. Sorry, this is not transpose. This is transpose. Okay, transpose. It is the matrix transpose, and then after we got the mat mul QK, so we will do the depth. Okay, we will do the attention logics, and then we will do with the mass if it is provided. If it is not provided, then we will just use the self attention logics, and then we will do with the attention width So after we do with the softmax to get the attention width, we will do another multiplication with the V. So this is the code to understand the step on the scale dot product attention. So this is example. Let's say I have the Alice, I have the array 1, 0.5 and 0.1. Is it is 0.4, 1 and 0.5. Could it is 0.2, 0.2 and 1. So what does it mean? In this kind of embedding, okay, this is the embedding. Alice, if it is in the index 0, so it is 1. And the remaining is lower value. Is if it is in the second or index 1, then the remaining will be lower and this one will be 1. Good. Let's say this is the word in the index 2. So it is 1 and the other will be less than 1. And this kind of embedding, it will try to look at the dependency Alice and is and Alice and could. So in this case, could is 1 and the word Alice has a kind of embedding or encoding 0.2. When there is a word is, okay, Alice shows 0.4 and could shows the embedding score is 0.5. Yeah, with this kind of values, you can do the attention. So we can get the Q. The Q means we want to combine the value from Alice, is, and could, and we are doing with the stack. I hope that you understand the stack. Okay, so if you learn the data structure and algorithm, yeah, we have the stack and queue. So in this case, we are just stacking the matrix of the embedding every of this factor, Alice, is, and could. And yeah, for this example, let's say, yeah, we assume that the k equals to the q and the v is equal to the q. Yeah, just for this example. So you can perform the dots, it's a scale dot product attention. So you can perform this scale dot product attention q, k, and v. So you can do with this mechanism. We will get the output and we will get the attention widths. Okay, this is the attention width. And this is the output. And after we got this attention, we can perform the decoder. So this is the attention width, and we will put this one for the decoder. Or inside the decoder, we can do another process to get the output. Now let's move on into the transformer. So we have the attention, and now if we want to put the attention into the transformer block. In the transformer block, we have several layers. So first, we need to initialize the width. Initialize the width means we will make the width as random. Random, and number of heads. So we need to define how many words that we want to pay to attention. For our example before, we have 3. Okay. So if you still remember about Buck. Buck is very cute. And he is a dog. Then we have the attention for Buck, cute, and he. Then if we have 3 attention, we can define the number of heads equals to 3, and so on. So we will do the initialization, and then we set up the feed forward. This is the feed forward layer. And after we have the initial state, we can also make the function for the multi-head attention. For the multi-head attention, we know that for every of this, for every of Q, K, and V, we will do the multiplication with the weight. So Q multiply with the weight of Q, K multiply with the weight of K, and V multiply with the weight of V. Then you can do the scale dot product. It means it is the matrix multiplication of Qi with the Ki transpose divided by the square root of the depth. And then we get the attention width. This is the exponent of the scale dot product. And then at the end, we will get the attention width, which is the summation for all the attention width. For the head, okay, we have the matrix multiplication multiplied by the V, and we put into a list. So this is a list. So every head will be in a list. After the loop, okay, after we finish calculating every of the head, we will do the concatenation. So we will combine every of the head, and we will do the multiplication with the dot product. With we will do the multiplication between the head and the WO, or this is the width for the output, and we will show the output. We can design the feed forward. So this is the design of feed forward with the ReLU activation. Okay. And then we can also do the self attention network. In this case, we have the multi attention in the XXX. So X, it refers to the data itself. We have the self attention. And after we have the output from the self attention, we can perform the multi-head and feed forward. So this is the basic transformer that I explained to you in. And let's say we have this sentence, Alice is good. Again, we have the embedding. So 1, 0 0.5, 0 0.2, 0 0.3, 0 0.7, and 0 0.1. This kind of embedding, actually, you can design. Let's say I have 3 words, and with the embedding dimension is 6. So then we have 1, 2, 3, 4, 5, 6. Yeah, you can have the embedded dimension like 9, 10. If you have a lot of embedding, of course, it will be computational cost. Again, after you have those embedding, you will stack of them and then perform the transformer. After you do the transformer, then we will get this transformer block. Okay. So we can apply, after we have this transformer block, you can do the prediction. What is the next possible word, or what is the next possible sentence, and etc. So I give this explanation. Okay, why do we have 6 dimensions of embeddings while there are only 3 words? So the 6 values capture various features or aspect of the words. Even though you have only 3, but there might be a kind of hidden features. Okay, sometimes we call it hidden features. Or in some literatures, they call it latent features. If there are some latent or hidden features, we can capture that one using the embedding. The 6 values capture various features and aspects of the words, such as its semantic meaning or syntactic role in the sentence. So, for example, if we have the word Alice, and this is the embedding. Okay, we have the word Alice 1, 0 0.5, 0 0.2, 0 0.3, 0 0.7, 0 0.1. The encoding might give you some information. For example, for the gender related features, maybe this one, it is representing the word Alice or the position, maybe. This one is a feature to represent that she is a female. Semantic association. So this kind of embedding might represent, okay, this is a human. Okay, maybe yeah, this one is a features to represent that Alice is a human. Syntactic behavior. So we want to check whether it is a subject or it is an object or it is a place, something like that one. Then yeah, those kind of things can represent its of the feature of one word. In the real word embeddings, you already learned the word to fact or birth. So we will learn birth next week. Okay. The dimensionality is often much larger. Yeah, I'm just giving you like 6, but in the word to fact, you can have a lot. And birth, you can have also higher. For example, maybe in this algorithm, we have 300 or 700 something. So it is to encode more nuanced information. So maybe if it is the word Alice, this person is not Korean. This person live in US or UK, and yeah, this person has a relation with some kind of movie and etc. So those kind of things, yeah, we can the embedding. Okay, the next one is only just to perform the transformer. It means we just reuse the existing library about the transformer. Yeah, as I mentioned to you, I will explain birth. Whenever you use the transformer, there is one of the library in Python, we can utilize birth. So we can tokenize any words with birth, and we can use the model, which is birth. In this case, we do not use the tokenizer from the sklearn. If the tokenizer from the sklearn, it is just to split the sentence into token. So in this case, we have one token about Alice. We have another token which is. We have another token a. We have another token great, and we have another token friend. So we have like 1, 1, 1, 1, 1 like that one. But with birth tokenizer, we will do with a kind of model. So they have the pre-trained model. And from this pre-trained model, we will do some kind of attention for every word. And the embedding will be a little bit different with the tokenizer embedding. So once we have this birth tokenizer and birth model, we can do the tokenizer. For example, yeah, you can use some kind of tensors. So the tensors here, you can use the PyTorch, you can use some kind of tensor, like I think I explained this one. There are some tensors. Oh, I didn't. Yeah, I have explained this one. If you use the PyTorch, you can use PT. If you use the TensorFlow, you can use TF. If you use NumPy, you can use NP, and for the GAX, you can use JAX. So just apply this one, and if you need to run this one, okay, I'm using the PT, which is the PyTorch, and input the IDs and follows with the model. And then you can do the output from this model and give the attention. After we got the attention, so you can check what is the attention width for the layer 1. So in order to run this, it takes some time because you download the library. For example, in this case, you will use the BERT. You will use the pre-trained model. The BERT pre-trained model is one of the famous pre-trained model, and you need to download it into your computer before you run it. And this is the attention width for the layer 1. And after you have the weight, then you can plot. For example, I want to know what is the weight here. Then we can get this kind of heat map. So how to explain this map? The higher value is the higher or more important for this sentence. If you have the CLS SEP, okay, so we will take a look more later about BERT, what is CLS and what is SEP. SEP is separator and CLS is a kind of text in BERT model. The higher number is the more important. Okay. And you can apply with the BERT visualization. Is using the same with the BERT. And we can visualize which text is more important. So Alice, you can see the importance. Color is a great friend. So we can check the importance of this word compared to the other words in the sentence. Okay, I think because of the time, I will explain more about this BERT together with the material of BERT next week. And this one is an example about GPT-2. Okay, so you can use the GPT-2 for free. If you need the GPT-2 for your modeling in your project, you can try to apply this one. Of course, the result is not as good as the current GPT, but you can use this one just for your practice because it's free. If you are using the ChatGPT, the current ChatGPT, you need to pay some money. Right? With this one, it's free. Okay. Okay, then I will finish. So I will continue the next material on next week. If you have no question, then we will finish the class. Suatu